All right, let's talk about something we've all run into. You build a Python script, it works perfectly on your small test data set, you're feeling good. But then you feed it the real world data, and everything just grinds to a halt. It's probably one of the most common and frustrating problems in data science. So today, we're going to break down the smart workflow that turns that sluggish, crawling code into code that absolutely flies.
And make no mistake, this isn't just about making your code run a little faster. As you can see from this quote from an engineer at Purple, this can be the difference between a system that works and a system that completely falls apart. We're talking about keeping the lights on. Choosing the right tool for the job isn't just a best practice. It's the bedrock of building stable systems that can handle the real world.
So what's the real culprit here? 9 times out of 10, it comes down to the fundamental tools we're using. And that default choice for so many of us, the simple Python list, has a high-performance counterpart that's just built for this kind of heavy lifting. But here's the secret. It's not about picking one over the other. It's about knowing exactly when to make the switch.
The best way to think about this is not as a competition, but as having the right tool for the right stage of the job. Think of a Python list as your super versatile multi-tool. It can do a little bit of everything. And think of a NumPy array as your high-powered drill. It does one thing, and it does it incredibly well. You wouldn't build a house with just one of those, right? Same goes for your data pipeline. And here's what that looks like in practice. The list, our multi-tool, is all about flexibility. You can throw anything at it, numbers, text, whatever, and it's fine. It's dynamic, you can add and remove stuff easily. The array, our power drill, on the other hand, trades all that flexibility for pure, unadulterated power. It demands just one data type, and it's a fixed size, because every single part of its design is optimized for one thing: ridiculously fast math.
This table really lays it all out. See that homogeneous data type for NumPy? That's the secret sauce. Because all the data is the same type, NumPy can perform calculations in super optimized C code, completely bypassing Python's slower, more general-purpose engine. And that right there is what leads to those huge speed gains, way less memory usage, and the ability to do math on your entire dataset at once, without ever writing a slow, clunky for loop. So the secret isn't picking a winner between lists and arrays. The secret is this simple but incredibly powerful workflow that gives you the best of both worlds. We're going to use the right tool at exactly the right time, flexibility when we're gathering our data, and raw brute force power when it's time to do the math. And here it is, the 3-step playbook. It's super simple. Step 1, you start with lists. When you're pulling in raw, messy data from a file or an API, nothing beats the flexibility of a good old Python list for getting it all in and cleaning it up. Step 2, the pivot. Once your data is clean, it's all structured, and it's purely numeric, you make that critical conversion into a NumPy array. And then, step 3, you hit the accelerator. With your data now in a NumPy array, you can unleash its full power for all your heavy-duty statistical analyses and mathematical operations.
So where does all this incredible speed actually come from? The magic word is vectorization. Now, it sounds kind of fancy, I know, but it's a really simple and powerful idea. Instead of looping through your data one piece at a time in Python, you just apply an operation to the entire dataset all at once. It all happens behind the scenes in that blazing fast C code, which just blows past the normal Python bottlenecks. And working right alongside vectorization is another brilliant idea called broadcasting. Let's say you need to add a single number to a huge array with 1 million elements. Instead of making 1 million copies of that number, broadcasting it virtually stretches that one number to fit the whole array without using extra memory. It's an incredibly efficient trick that saves a ton of memory and makes your code way cleaner.
Okay, that's all the theory, but what's the actual payoff? What do you get for doing this? Let's look at the hard numbers, because the performance gains from this workflow, they're not just small improvements. They are genuinely transformative. Let's start with memory. By getting rid of all the extra overhead that Python lists need for each individual number, NumPy can cut your memory usage by as much as 86%. Now, for a massive dataset, that's the difference between your analysis running smoothly and your entire machine crashing. And now for the main event, speed. That code that was crawling before, using this workflow, you can see vectorized NumPy operations running over 20 times faster. That's not a tweak, that's a total game changer. This is the direct solution to that problem we started with. But the really critical thing to see in this data isn't just the 20x speedup. It's the consistency.
Look at that. It doesn't matter if we have 1,000 elements or 1,000,000 elements. That 20x improvement holds steady. This is what scalability looks like in the real world. It means you can have confidence that your code's performance is going to hold up as your challenges get bigger and bigger.
So why are we making such a big deal about this? Because this workflow, it isn't just another tip or trick you pick up. It's a foundational principle for anyone who's serious about building things with data. Let's just zoom out for a second and see how central this really is. Here's the bottom line. NumPy is basically the engine that powers the entire scientific Python world. I mean, every major library that you rely on day to day, pandas, scikit-learn, even the heavy hitters like TensorFlow and PyTorch, they are all built directly on the speed and efficiency of NumPy arrays. So mastering this list-to-array workflow isn't just about learning one library. It's about becoming fluent in the fundamental language of modern data science and AI.
So if there's one thing to take away, it's this. Adopting this workflow is what separates amateur code from professional-grade engineering. It's that conceptual leap you make from writing a script that just works on your laptop to designing a system that scales beautifully out in the real world. Which leaves you with one really important question to ask about your own projects. Your code might work today, sure, but is it really built for tomorrow? Is it built to scale? Thanks for watching.